All right, it is that time of year again. We are here for the AP Physics C mechanics free response questions. As far as it looks like, they've only actually released one version this year, which I guess is kind of good news for me because trying to record four videos in one day in years past for mechanics and E&M really got tiring and draining. It took me like 4 hours to get everything done and uploaded, but yeah, today should be relatively quickly. It's four questions, and from what I've heard, that these mechanics questions are actually not too bad. To my disappointment, I've heard that there's almost no calculus on any of these, which seems kind of like a strange design choice, given that this is AP Physics C mechanics, and not AP Physics 1. But yeah, we'll go ahead and see what we have in store for us. So. In this first question here, you've got two blocks and they slide towards each other. You've got some speeds, speed 2, 0, and speed of v 0. One of them is 6 times as massive as the other. This is definitely going to be a momentum question. A part 1 says that you have to draw the momentum vectors before and after the collision and relative magnitudes and all of that good stuff. So let's go ahead and take a look. I assume that the diagram is on the next page. So I'm going to go ahead and flip that and yep, there it is. Okay, so momentum before collision, momentum after collision. So block 1 had a mass of m and a speed of v0, 2v0. Hence, it has a momentum, 2 units of momentum. The other block has a mass of 6m and a speed of v0, but it's to the left, which means that it's going to have -6 units of momentum. 3, 4, 5, 6. Since momentum is equal to mass times velocity. Now, after the collision, both blocks should be moving together. And because this is a collision with no external force, total momentum is going to be conserved. So the two-block system should have 4 units of momentum to be left before the collision, and then 4 units of momentum after the collision. So there we go. There's all of our momentum vectors already. Pretty easy. All right, part 2. During the time interval before the collision, you have a force that is exerted like this. This doesn't seem fun. Actually, maybe this does have some calculus to it. Okay, force is exerted on block 2 by block 1, modeled by that. And F max is the um magnitude of the maximum force during the collision. Derive an expression for X max. Okay, so this is definitely an impulse question, but let me actually go back to the first page. I need to read some more stuff again. Collision occurs from 0 to TC. Okay, yeah, I don't know why I needed to read that. Okay, yeah, I should have read that initially. The collision happens during the time that this force is exerted, which I guess should have been pretty obvious. So this is definitely saying that impulse, which is equal to integral of f of t dt from 0 to tc, is equal to change in momentum. Now, since this is the force on block 2, this is going to be the change in momentum for just block 2. So we're going to actually have to find their velocity after the collision to figure out the change in momentum for just block 2. Yeah, so let's go ahead and do that real quick using conservation of momentum. So we have m1v1 plus m2v2 is equal to m1 plus m2 times their final velocity. So that is going to give us 2mv0 minus 6mv0, which is, like we thought, -4mv0. And that should equal the sum of their masses, which is 7m times final velocity. So the final velocity is going to be -4/7 times the initial velocity. That means that the change in momentum for block 2 is going to be given by its mass, which is 6m, multiplied by the final velocity, -4/7 v0, minus the initial velocity, so plus v0. Keep in mind that momentum is a vector. So we do actually need these vector signs. That means that the negatives do matter in this expression for impulse and obviously for the expression of conservation of momentum. So that's going to give us 6m. Negative 4 plus 7 is going to give us 3. So we're going to get 3 over 7 v0, and therefore 18 over 7 m v0, assuming I did my math correctly there. Okay, so that tells us that integral from 0 to tc of f max sine of at equals dt equals 18 over 7 mv0, while integral of sine is going to give us a negative cosine. So we're going to get negative f max over a times cosine of at from 0 to tc equals 18 over 7 mv0. So then that is going to tell us that negative f max over a times cosine of ATC minus cosine of 0, which is 1, equals 18 over 7 mv0. This is not hard. It's just tedious. Yeah, okay. So, all right. That means that F max equals, okay, 18 mv0a over 7, 1 minus cosine of ATC. Yeah, what the heck is this? Yeah, this is so tedious, but using algebra, if I did that algebra correctly, which I think I did, that's what we should get for F max. Fun. Okay. All right. Consider a new scenario where block one initially slides in the x direction and block two starts in the negative x direction with a constant speed of v0. They then stick together. And the two block system has a constant speed of v0 after the collision. Okay, so part B is kind of implying that that the two would be moving to the right. Um, Block one initially slides in the plus x direction with a constant speed of v1, and block two has a constant speed of v0. Yeah, I think that when the two blocks stick together in part B, they would have to go to the right. Otherwise you're not going to have total momentum being conserved, which is fine if there are external forces, but there doesn't seem to be in part B. Okay. So I'm going to go ahead and clear these, and we'll go ahead and take a look at part B. Part B, I think you want to start with conservation of momentum again. So you'd have m1 v1 plus m2 times negative v0 is equal to m1 plus m2 times v0. And where does that come from? That comes from conservation of total momentum. So then that tells us that you have mv1 plus 6m times, or negative 6m v0 is equal to 7m v0. So mv1, yeah, this actually does give us something. Okay, well, I wasn't quite sure, but I mean, I guess it had to. So v1 has to equal 13 v0 then. Yeah, easy. So just a normal conservation of momentum problem. There we go. All right, that's question one. I don't even know how long that took. I'm kind of curious. I can't see how long I've been recording for right now. Okay, great, whatever. Let's go ahead and take a look at question two now. So question two, you've got two springs. They're both on opposite sides of the block. This kind of looks a little bit tedious as well. Spring constant A and a spring constant of that 2K, spring constant of K and a spring constant of 2K. Each spring is relaxed, and then you move it to X1. So spring A is going to stretch and spring B is going to compress. All right. So in the energy bar chart, okay, so we have two spring potential energies as well as kinetic energy of the block, and we have to draw when you have the block held at the position of x1. So it's held at rest, which means that there's no kinetic energy. So that one's pretty easy. No kinetic energy. So we'll just say that that one is 0, right? Whereas for the other ones, we have to make use of 1/2 kx squared. Both of them have the same x value. It's the k's that are different. So we can say, for example, that since the spring A has a spring constant of just k, then maybe we have just this much potential energy. Well, then that means that you should have 2 units of potential energy for spring B because it has double the spring constant then. Yeah, and they're both positive because spring potential energy is always positive or 0. Okay, block is at rest at x1 and begins to oscillate. Derive an expression for the speed. This is easy. It's just conservation of energy again. So we can start off by saying that initial energy is equal to final energy. What does that give us? Well, that gives us 1/2 k x1 squared plus 1/2 times 2k x1 squared. Those are our two spring potential energies. Um, UBI equals the sum of all of our energies at the end. So you're still gonna have some spring potential energy in both springs, but now you're also gonna have some kinetic energy. So you're gonna have 1/2 k times x1 over 2 squared plus 1/2 times 2k times x1 over 2 squared plus 1/2, and I think, yeah, mv squared. We have to obviously find v then. So I'm going to draw this or keep writing up here. So you've got a 1/2 kx squared plus a 1kx squared. So that's 3/2 k x1 squared on the left. And then on the right side, you're going to have an eighth for the first term, and then you're going to have a fourth, so that's going to give us 3/8. So 3/8 k x1 squared plus 1/2 mv squared. Let's cancel one of the 2's out. So that's going to give us a 4 here. So 3 minus 3/4 is 9/4. So 9/4 k x1 squared equals mv squared. Pretty easy to solve for v then. V is going to equal, yeah, 3/2 x1 square root of k over m then. There we go. Not too bad, just conservation of energy. All right. Okay. Perfect. So let's go ahead now and take a look at part C. Where's part C? There it is. Oscillates with period. Let's get rid of all of our text again. Block oscillates with period t, and you are given the stuff here. So yeah, that's pretty simple graph. Let's go ahead and just move on to the next page. All right. In scenario 2, you have the same surface and there is friction, and it completes multiple oscillations with the same period before coming to rest. And you have to draw the kinetic energy as a function of time. So it's still going to start at rest. It's still going to start with no kinetic energy, but it's just that you won't go up to the same amplitude every time. This is actually pretty easy. Velocity would be a normal sine function with like an exponential decay, or some sort of linear decay, actually. So we could expect the kinetic energy to look something like, oh geez, I'm so bad at drawing. But let's give it a try. So it's gonna look something like this. It's supposed to, what I'm trying to draw is like a sine squared graph, and I think you guys can probably see that. That is like decreasing in amplitude every time. It's supposed to be decreasing amplitude every time. We know that because friction is present, and that means that total energy or mechanical energy will not be conserved, so it should not reach the same speed every time it passes through equilibrium then. You should start with 0 kinetic energy because you start with 0 speed, and then every half period you're going to have 0 speed because you're at the end point or amplitude of your oscillation. So something like that then. Okay, it's just a sketch, so I don't think they're going to really be any pickier than that. Okay, scenario 3, you have a larger mass and you keep the same coefficient of friction, and yeah, you have to describe how one feature of this would change from the figure that we just drew. Okay. How does one figure change if you have a bigger mass? The period is going to change. Yeah, it's a duh. Yeah. This is not this is kind of easy. I'm a little bit sad. I wish that I had a little bit harder question. Period is equal to 2 pi root m over k. That is actually going to hold regardless of whether you have friction or not. So since you have a larger mass, uh, each period would be longer. So the sine squared graph would yield wider uh how do I say this? Wider mountains and valleys is what I'm trying to say. That's not really a mathematical term. Wider oscillations relative to time, I guess. Yeah. Okay. Yeah. It's just that the period would get longer. So your graph is going to become wider. So, okay. Not bad. All right. Next question. You've got a pendulum, it looks like. Center of mass is at a distance of h. There's negligible friction. The rod collides with a rigid stopper when it's at the lowest point, and then it comes to rest, and the block is launched horizontally out of the box. Oh, I thought this was just going to be a pendulum, but no. Wow, okay. The block moves along a horizontal surface towards a motion sensor that measures the speed, and you have to find the acceleration due to gravity with a motion sensor and a meter stick. Oh no. This is also easy. All right, describe an experimental procedure. Let's create an equation to go along with this. You've got conservation of energy and yeah, the box stops. So conservation of energy says that the mass of everything, what's got negligible mass? Let's see. The box has negligible mass, but the block does not. Okay, that makes this ridiculously easy then. So that tells us that mgh, where m is the mass of the block, is equal to 1/2 mv squared, which you can measure v with the motion sensor and measure a with the oh no. Yeah. You can measure H with the meter stick. Mass cancels out and yeah, that's it. All you have to do is measure height and velocity of the box, height that the block starts at, and velocity of the block. Why is it box and block? Why can't it be two different words? Uh the velocity of the block when it's going horizontally. That's it. And then to take steps to reduce experimental uncertainty, you can displace the block different heights and measure the speed accordingly then do multiple trials doing that, right, with different heights and measuring different speeds. I'm not even going to type that out. That's so easy. Describe how it could be graphed. Well, we already have our equation. We're measuring speed and height, right? So if you wanted to calculate g, you need to have some sort of linear thing with that, right? I'm just going to graph speed squared and height. You could also do speed versus square root of h because v is equal to root 2gh here. Right, I'm going to stick with the v squared and h one because that's better. V squared is equal to 2gh. That tells you that v squared over h is equal to 2g, which has to be your slope because that's rise over run then. So plot v squared and h, and then find the slope, and then divide that slope by 2 to get g. There's part B done. All right, really quick. Okay. Next situation, you have some sort of related system with friction, it looks like. Okay. There's coefficient of friction, it's a rough surface, and it's probably gonna stop. Yeah, it comes to rest, and then you've got the height that the block started as well as X max, and you have to determine stuff to measure the coefficient of friction. That's also very easy. Why? Because all of your initial gravitational potential energy turns into thermal energy. How do we find thermal energy? It's force of friction, which is coefficient times normal force multiplied by X max. And whoop-de-doo, mg cancels. So you've got H is equal to mu X max, which means if you want to find mu, you could plot H versus X max then. And you're just going to get a straight line where your slope is literally the coefficient of friction. Okay, H, X max. Um, I feel like you guys can probably plot the data, but so I'm not even gonna attempt to do that here. Yeah, because I can't see the data points when I actually go to this graph. However, this already tells you what to graph. Put H on the vertical axis and X max on the horizontal axis. Here are the things that I want to point out about this question, though, in order for you to get points. When you go over to your graph, obviously, you're going to have to plot the data points and you are going to have to plot them correctly and draw a best fit line. Other things you have to do is you have to actually scale your axes. And this is kind of bad because there's no like major grid lines. They're all the same shading. So you actually kind of have to like count and, estimate. You want to fill up half or more of this grid space with data points. So you actually have to put numbers on both of your axes. In addition, you put H in terms of the units that you have, and you put X max, and you put units. And then again, you plot your data, put numbers on the scaling, right? Plot your data, create a best fit line. And then, like we said, the slope is going to equal the coefficient of friction. So say that you draw a line and say that that line does not look that bad. Let me just go ahead and create a random line right now. Obviously, I haven't plotted my data, but this is just to show you what you do with your line once you have it. So here's our line. To find the slope, you have to estimate 2 points. Here's 1 point, here's another point, right? And how do you calculate slope between 2 points? It's rise over run, the change in y versus the change in x. You say what numbers those are, you calculate the slope, and that's your coefficient of friction, and question 3 is all done. All right, move on to question 4. And this is the one that I've seen a lot of people say that they hated. Let's see how it is. You've got a disc and a ring. The ring has higher inertia than the disc. I can already tell you that. Mass R, mass M, excuse me, radius R, and they are both rolling without slipping, which is good for us because that means that the angular and linear speeds are connected to each other. They smoothly transition to a ramp. Okay, so they both have the same speed. They smoothly transition to a ramp and they continue to roll without slipping. The ring travels a farther distance. That does make sense. Let's see, you have static friction force on each and indicate whether the force of friction on the disc is how that relates to the force of friction on the ring. Well, they both have the same gravitational force, and if you draw a free body diagram for these, they're going to have gravitational force, friction down the ramp, based on how they're rolling, as well as normal force. Now, I'm not actually showing you where these forces are being applied because it doesn't matter here. All you have to note is that the disc slows down first, which means it has a bigger acceleration, which means it has to have a bigger friction force then. Yeah, and that's my justification, right? The disc stops earlier. They both have the same speed. It goes less distance. Kinematics says that means that there is a higher acceleration, which means that since they both have the same gravitational force, there is a higher friction force. There you go. All right. Okay. So cylinder, you've got an man. They're not even. They're just leaving inertia as I. Okay. The cylinder rolls up a ramp without slipping, and you have to actually find static friction. Okay, so there's a couple of different ways that we can do this. Pick your poison. You have to use net torque and net. You don't have to use net torque and net force, but I'm going to because that's how I like to think about forces, especially with rotation. So, what our net force tells us is it tells you that sum of all forces is going to equal I times alpha, which is going to equal I times A over R because this is rolling without slipping. Not, wow. Okay, I really messed that up. Oh, geez. Net force is equal to MA, and then sum of net torque is equal to I alpha, which is equal to I A over R. My apologies. I don't know how I messed that up. Okay, there's our two equations that we're going to have to start with. Well, net force is going to be given by sum of the component of gravity going down the ramp plus the static friction force, and that'll equal MA. Meanwhile, for the torque, it depends on where you set your axis to be. you can choose your axis wherever you want. I am going to set my axis to be the center of the object. That means that friction force, and you can maybe see me writing in the lower left-hand corner, but that means that the torque due to static friction is going to be given by radius times friction force, and that's going to equal IA over R then. Or in other words, F, or not F, in other words, A is equal to R squared F over inertia. Plug that back in to our net force equation. You've got mg sine theta plus F equals m r squared over I times F. Yeah, and that's going to tell you that F is going to equal, m's are going to cancel, so you're going to get g sine theta over r squared over I minus 1. Wait, the m's don't cancel. What am I saying? Mr squared and mg sine. Yeah, there's no m in that other term with just F. So yeah, this is your answer for friction force. You've got m, r, I, theta, and physical constants. We're all good to go. Okay. In a different scenario, the center of masses have the same initial speed, and now they do slip, and you have to indicate whether the kinetic friction force on the disk will be greater than, less than, or equal to magnitude of kinetic force exerted on the ring. And okay, so they both have the same mass, which means that they should both have the same linear acceleration. And if they have the same linear acceleration, uh, then we have to compare angular acceleration. So they both have the same forces. Wait, should this not just be equal? They have the same mass. Hmm. Yeah. This this has to be they have to be the same. I'm pretty sure they have to be the same magnitude. Uh because now we cannot say that A is equal to alpha R or V is equal to omega R since they're rolling without slipping. So, yeah, I mean, kinetic friction, that none of that matters. It's just kinetic friction is equal to the coefficient times normal force, and both of them have the same normal force. Yeah, since they have the same mass, same gravitational field, and same angle. That's it. Wow. Really? Come on. Wow. These are so much nicer than last year's and previous years, but I'm also kind of a little bit disappointed. I kind of wish that they were a little bit tougher, a little bit more calculus perhaps, but yeah, I mean, we're all done already. I don't know how much time that was. It doesn't feel like it was any more than half an hour. It might have only been like 20, 30 minutes. So, thanks for watching, guys. Hopefully you found this informative. Tomorrow I'm going to take a look at the E&M questions. So I'll see you there, hopefully.